Okay, we're going to take a look now at the one-to-one property. And the one-to-one property is basically our way of saying that we have one-to-one functions when we have exponential functions. And that really comes from the fact that exponential functions, because they're always increasing or always decreasing, they're always going to pass that horizontal line test. They will pass both the vertical and horizontal line test, so they're going to be one-to-one functions, which means that if we have the same input value, the output value should be exactly the same, and vice versa. If we have the same output value, the input value should be the same. And that leads us to the property that if we can get them written so that they're both in exponential form, then the statement that a to the y and a to the x are equal is equivalent to saying that x and y are equal. So I can go from one to the other. So the way we use this to solve exponential equations is that if it's possible to write them so that they have the same base, then we can just say that their exponents are equal. So let me show you what that looks like for example A. For example A, the base that would be easiest to work with here would be if I can get them to both have base 4. And that's easy enough. I can write 16 as 4 to the second power. And then I just keep this as base 4. And by the one-to-one property, I can conclude that 2 is equal to x plus 3. So it's not that I got rid of the 4 on both sides, it's that the fact that these two are equal means that these two are equal automatically. And therefore, I can simply solve this and get x is equal to -1 for my solution. Now this only holds when we have a is greater than 0 and when a is not equal to 1, which is true for both parts b and c. So let's look at a couple more examples. I think that in this case, rather than trying to get 27 written as 1/3 to a power, it would be easier to rewrite this as 3 to the -1 to the x. And then to rewrite that as 3 to the -x. And now our goal isn't to get 27 written as an exponent of 1/3, it's to write it as an exponent of 3, which is an easier question. And now that means that these two are equal. So if these two are equal, then therefore we can conclude that their exponents have to be equal to each other as well. So we can say that this implies, by the one-to-one property, that -x is equal to 3. Therefore, x is equal to -3. And we'll do similar work over here, where we can say, well, I can write 1/32 using base of 2, if I can write it as 32 to the -1, which is the same thing as 2 to the 5th to the -1, which is the same thing as 2 to the -5th power. And therefore, since 2 to the 4x plus 1 is equal to 2 to the -5th power, then I can say that this is equal to this. So we end up with the exponent, 4x plus 1, is equal to the other exponent, -5. And now I get to solve that, which leads me to 4x is equal to -6, which leads me to x is -6/4, which reduces to x is -3/2. So therefore, we are able to solve all these exponential equations simply by getting them to the same base. Now, this is not going to apply for all exponential equations that you ever come across. We're going to find that after we learn about logarithms, we often are going to use logarithms to solve exponential equations. However, when we can get them to be the same base without it being too much work, this is a nice, elegant way to solve those problems. All right, our next topic is transformations of exponential graphs. And this is really just bringing back some of the content that we were studying back in Unit 1. I believe it was section 1.7, somewhere around 1.6, 1.7, I believe, where we were looking at how can we take a parent function and then transform that parent function. And the first thing I encourage you to do is take a look at whether they are horizontal operations or vertical transformations. So this is on the inside, so it's horizontal. This is on the inside, so it's horizontal. This is on the inside, so it's horizontal. Whereas these are on the outside of the function, and so therefore these are vertical transformations. Now, let's do the vertical transformations first. For vertical transformations, remember that if we add or subtract a number to the outside, then that's a vertical shift. And if it's a plus, then it's up. If it's minus, it's down. So this is a vertical shift up 5. With this guy right here, we're going to be doing a reflection. And we already said that it's on the outside, so it's a vertical reflection. Well, a vertical reflection is a reflection over the x-axis. And if we go over to our last vertical one, it's multiplying by 2. So this is a vertical stretch by a factor of 2. Now, if we look at the horizontal transformations, then those have very similar, shifts go with addition and subtraction. The negative sign makes a reflection. The multiplying makes a stretch or compression. Just remember that all the horizontal ones are sort of doing the opposite of what you'd expect. So for this one, this is going to not only be horizontal, but it's not going to shift you left 3 the way you might expect, because horizontal is always opposite of what you expect. So it's a horizontal shift right 3. And for f of negative x, that's going to be a horizontal reflection. In other words, over the y-axis. And this last one is going to be a horizontal, and you would think it would be a compression because it's times 1/3, but remember horizontal is the opposite of what you expect. So this is a horizontal stretch by a factor of 3. And what we're going to do now is take that into our use to describe what's happening to the graph if I give you an equation of a function where the parent function is now an exponential, and we're going to describe how it's getting shifted.